It's that time of year, Geometry Regents Review, and today we're going to be looking at similar figures. In our table of contents, we have things like identifying and applying the properties of similar polygons, applying three theorems to establish proportionality, and apply properties of similar right triangles. Now, within that context, we will not be doing or focusing on any types of proofs today. So let's take a look at what similar figures are. Similar, with the little squiggly symbol to represent similar, means that two shapes have the same shape, not necessarily the same size. So to identify similar polygons that are the same shape, we look for corresponding parts. Corresponding angles are congruent and corresponding side lengths are proportional. The ratios of the sides are proportional. In this first example, we have two triangles, triangle ABC and triangle DEF, and it's given to us to be similar. We establish a correspondence based on the ordering of the letters in the symbol. A is congruent to D, B is congruent to E, C is congruent to F, and the sides that are opposite or across from those congruent angles are called corresponding sides. Angles that are congruent in all three cases there will make the two triangles similar. There are certain criteria that make triangles similar, but we're not going to go over those criteria today. Now, making the ratios of corresponding sides, here we can do a number of different combinations where we match corresponding sides in the fractions or in the ratios. Pairs of corresponding sides are equal. So 12 over 6 is the same as 10 over 5. Or if we maybe make the proportion 8 is to 10 as 4 is to 5. That also is a set of corresponding parts. 8 is to 12 as 4 is to 6. So we can find a number of different corresponding ratios that are equal. In this particular example, we're going to determine if the polygons are similar, and if they are, write a similarity statement. Step 1 is to try to match the corresponding sides. And the way that we can do this, if we're not sure about which angles are congruent to each other, we match the smallest side to the small side and the largest side to the largest side. All right, so in the two triangles, I identify what the largest sides are and what the smallest sides are. Now, we're going to check to see if the side ratios are equal, and if they are, that means that the sides are proportional, or the triangles are similar. So we'll set up a ratio here. 2 is to 2.3, matching corresponding sides of the two large sides, as 1.4 is to 1.6, the corresponding smaller sides. When we cross multiply to check if this equation is true, in this particular instance, we get something that's close but not quite equal. One side gives us 3.22, where the other side is just 3.2. Not exactly equal. Close, but they have to be equal in order for this to be true. So in this particular case, no, the triangles are not similar to each other. In the second example, we have some angles to work with, and so because the three angles inside of a triangle always add up to 180 degrees, we can fill in the missing parts or the missing angles in these two triangles and then determine whether the two triangles are similar. But what we're going to do is we'll look to see if the triangles have congruent angles. That means that they're the same shape. So filling in the missing angles here, we get 75 degrees for the smaller triangle and 48 degrees for the larger. And now we can match angle to angle, the corresponding congruent angles, and we can determine by yes, all three angles are congruent to the other three angles, the triangles are similar, and we match the corresponding triangle statement in order in the same way we would the corresponding parts. Now, there are several examples where you can try by yourself, and we're not going to go through all the examples I show here, but most of them. So when there's not a diagram given, you want to draw a diagram. So we're going to draw a diagram and we're going to label it. Using the ordering in the symbolic way of writing that the two triangles are similar, we get an ordering. ABC is to ZXY. and filling in the corresponding values that they give us, and we're looking to determine what is the measure of angle y, we simply have to do a little bit of homework and play the matching game between the two triangles and their angles. We match their corresponding angles. The missing angle here is 35 degrees. Pretty easy. Here, in triangle DEF, similar to triangle GHI, the measure of angle G is 110 degrees, the measure of angle E is 25 degrees, and they want to find the measure of angle F. Now, we can do this without a diagram as long as we use a corresponding parts little key here that I've created for myself to know which parts are corresponding and which angles are going to be congruent. And doing a little math with the fact that the three angles in a triangle add up to 180 degrees, you can solve a lot of these similar triangle problems. Now in this particular example, we're going to see two quadrilaterals, two four-sided shapes, in which their four angles will always add up to 360 degrees. And going by the way the letters are corresponding, A goes to E, B goes to F, etc., we can fill in some corresponding parts. The side that matches with 6 and 9 go together, so we can create a ratio of corresponding sides, and then start building the ratios for all the other corresponding sides. We'll also be able to fill in a lot of these missing angles as well. Now 6/9 is a fraction that we could reduce, and you can also leave it as is, but we can use that because it has both numbers in the fraction. And in the rest of these fractions or ratios, we have a missing value. So we're going to use 6/9 as our base to work off of, and each one of these fractions will use a proportion to solve. All right, so our proportions are always found by setting two fractions equal to each other and then cross-multiplying to get the result. Here we're just going through and doing a little bit of cross-multiplying and dividing to find the missing values, x and y, or fg and gh. And finally, we can find the last value, eh, or what I've dubbed z, by the last proportion, cross-multiplying and dividing. And yes, you can see some of our values do come out to be decimal values, so don't be afraid to embrace decimal values. Now, setting up a correspondence table between the angles, we can start matching what values are equal to each other. The ones with the boxes indicate 90 degrees, and finding the missing angle, in which all four angles have to add up to 360, we find that other missing angle to be, let's see, 360 minus 290 gives us 70 degrees. All right, so we can write in all the missing angle values now. And we've completely solved the similar quadrilateral problem. And similar figures are similar because their angles are congruent or equal. That's what it means to be have two objects to be the same shape. They're not the same size, otherwise we would say that they are congruent to each other. But the angles always remain congruent. It's the size of the sides that change, but remain in proportion. Now the perimeter of one object in ratio to the perimeter of the other object is going to be exactly equal to the ratio of two corresponding sides. So since the ratio of two corresponding sides here was 6/9, or we could actually reduce that to 2/3, we can find that the perimeter ratio is exactly equal to the ratio of the corresponding sides. So that's something to note. It's not the same with area and volume when we get into higher dimensional shapes, but here perimeters are the same ratio as the ratio of the sides, because both of those are linear measurements. And these ratios that we find are often helping us find something called the scale factor, how big or small one object is in comparison to the other. Check out this exit ticket problem here with two triangles and a multiple choice. Find the length x. All right, so all we do is first match corresponding parts in the way that they've drawn the triangles. They are matched in the way that they are oriented. So finding the corresponding parts is pretty easy. Setting up a ratio is pretty easy. And also cross-multiplying to solve that ratio is also pretty easy. So just takes a little bit of practice and maybe a calculator, but you've got this. Fractions aren't that bad. And you are going to sometimes get decimals. So embrace the decimals. Here are a few practice problems that I suggest you do. This will be included in the packet that I have with the Regents Review. So these will be questions that I won't go all over together today, but something that you could use to practice that are similar to what we are doing. I do want to focus on problems that look a little bit more like Regents level questions. And so here, let's just take a look when we have two triangles that are similar and they say that that's given. That indicates a number of things. Number one, that their corresponding parts or their corresponding angles are congruent. So we can mark them accordingly in the diagram. And we can then also say that the ratio of the corresponding sides are proportional. Now, working out some of the details, they give us some values which have mostly been inputted into the diagram for us, but you always want to check and you may have to add things to your diagram. And making a list of the things that I know and the things that I'm trying to find. And I know I'm trying to find VT, all right, so I might label that as X. And now making a comparison of corresponding sides, and my ratio that I would use to solve a proportion is always going to be used to solve for sides in a similar triangle or similar quadrilateral or similar figure problem. And here we get X equals 7.5. VT is 7.5. Always state, if they're asking you to find the specific thing, make sure you state as your answer that specific thing. The triangle proportionality theorem apply three theorems here. So we're going to have a couple of different theorems that apply to the proportionality of triangles that also pop up in maybe some unexpected or maybe expected places. So check this out. Again, we're just going to warm up with two triangles here that are similar to each other, finding X and Y. All right, X is a side, Y is an angle. All right, so we're going to match ratios here to find the sides, and we're going to find corresponding angles to be congruent. So these are pretty standard questions, and so pause the video if you just want to like really carefully skim through what I'm doing here. I'm just kind of doing more repetitive of the same type of problem, matching corresponding parts, drawing a diagram, visualizing it, labeling it carefully, and then going ahead and trying to answer the question, stating the things that I know and writing down the things that I want to know. Perhaps even if there's an equation that I can write down, that would be a good thing. So when we're showing our work in a Regents type problem, like this one might be a part 2 question, you want to visualize, diagram, clearly indicate what you're doing so that the grader, the person who's going to give you the points for this, can give you as much credit as possible for having nice organized work that they can find. And so again, this is just about practice. When it comes to the Regents, this is practice. This is not a video that is designed to teach you this all over again. This is just to review what's true. This one in particular, the side splitter theorem, is pretty important in that if you have a parallel line to the base of a triangle, it's going to split the two sides into proportional parts. All right, so the parallelism of those two, the side and that other little chord inside there, if you want to call it a line segment, those two things have to be parallel in order for all of this to be true. So I'm separating these two, actually both sides, into 4 parts here: part 1, part 2, part 3, part 4. And using a little bit of the notation we should get used to using with like AB and BC, I'm just showing a proportion that's true here. The two sides on the left, if we make a ratio out of them, and the two parts on the right, if we make a ratio out of them, will be equal in this side splitter theorem. So to apply this, let's take a look at a sample problem where we have to find a missing side, which I've labeled X, and just matching these quickly, these corresponding parts, because we have parallel lines, we can make a proportion, cross-multiply it, and solve pretty rapidly. So these problems are not calculationally challenging. They are conceptually challenging for some, because there's a lot of details to look at. Which part matches with which part? So sometimes they give you the whole side, and sometimes you have to pick apart parts like I'm doing in the second example. And sometimes there are algebraic expressions involved where you might have to use a little bit more of your algebra skills to solve the equation. A proportion is ultimately an equation. All right, so this equation, a ratio equal to another ratio or proportion, cross multiply, but make sure you distribute, especially when you have binomials involved. And for this particular problem, you want to make sure that you're carefully looking at what type of an equation you're solving. All right, and here we get a fraction, which is preferable, but we can write it as a decimal as well. All right, so I'm going to go through a quick sample of some other problems here. This one, we have the two sides are parallel. It mentions that here in the problem. So we're just going to go ahead and set up the proportional sides using the side splitter theorem. I'm not even going to set up that chart right there. This is just way too easy. So they tell us some of the values in the problem, and I'm going to label the diagram carefully. So AE is 3, we have DC is 15, ED is 6, there it is, and the length of EB is what we're trying to find. So we're going to label the thing that we're trying to find as X, right? And so we're going to set up, in this case it's a little bit tricky because the side splitter involves the two sides of the triangle, not those bottom parts. So what we have to do is actually visualize the small and the large triangle here in order to get the value of the X here. All right, so we're making a picture of the small triangle, labeling the sides 3 and X. We're making a picture of the larger triangle, which has 9 and 15, again 9 coming from 3 plus 6. And setting up this problem, we get X equals 5. Again, like calculationally, this is not that challenging. Setting up the visual picture and the labels, that's the challenging part for most students. EB is equal to 5. I stated what they asked me. Parallel lines can also create, when you have two transversals, proportional parts. Okay, so when you have 3 parallel lines, all right, the parts that are in between the 2 parallel lines that have been cut up proportionally, here I could call them part 1, part 2, part 3, and part 4, they're going to be also in ratio to each other and proportional. So part 1 over part 2 is the same thing as part 3 over part 4. And we could also make a relationship horizontally as well across between the 2 parallel lines in each case. So as long as you match corresponding parts, and also consider some problems might include the entire length between the first and the third parallel line, you can set up ratios just as well, thinking about the fact that these are like triangle side splitter problems. All right, so here we have the 3 parallel lines. Like the side splitter part, we can set up 2 ratios pretty easily from the left and the right hand side, and solving that proportion works out to be X equals 15 in this case. Noting where the parallel lines are will help you find the proportional parts, so just carefully looking at the you try it problem here, carefully setting the ratios up. I don't think you're going to mess this up. Now the third theorem that's usually applicable here is that if you have an angle bisector, now recall an angle bisector cuts an angle into 2 equal pieces, so angle 1 and 2 here are equal. But the adjacent side to angle 1 and the adjacent side to angle 2 are going to be proportional to the sides that are across from those 2 angles 1 and 2. All right, so look at how I've labeled the diagram there and watch how I do this in an example. Again, pause the video when you're having some trouble following, because this is meant to just kind of give you a quick, rapid review, and there's a lot of material to cover here. All right, so in this particular triangle, again, we just find the congruent angles, match the adjacent and the opposite sides, and we're good to go. Set up your ratios, maybe a little bit of algebra may be involved into solving. Reduce fractions when possible, and just carefully take your time. Calculate your values. Use your calculator. All right. Now, a challenge problem might be because not of the conceptual idea, but maybe the algebra might be involved in solving it. So here, you get some quadratic equation to pop out of the proportion. And if you're not familiar with solving a quadratic equation from algebra, you have to do this by factoring. So you bring all the terms to one side of the equation where it's equal to 0, And then the last number on the end there, the negative 24, that's the product of the two numbers in your factors that you're going to use. And the negative 5 in the middle will be the sum of the two numbers you're going to use. Here we get numbers that will have opposite signs. One's 3 and one's negative 8. And making the factors x plus 3 and x minus 8 equals 0. What we're doing here then is we're solving the equation by setting each factor equal to 0 and solving for x. Now, since x here represents a length, we reject the negative value that comes out of this. In another context, we might consider keeping the negative values. So use the packet that I've included to summarize these ideas and practice the other problems that we don't go through in the review. Here again, an exit ticket that's reminiscent of a Regents question. It's a multiple choice question, but you still have to work out some of the details. You could try a little bit of guess and check, but if you don't visualize the problem, it's probably going to be hard to do that. So I've separated this into two separate triangles to sort of sort my ideas out, set up my ratios with corresponding parts. 2 over x plus 2 equals 9 over 36, and reducing the fraction to 1/4 makes it an easy problem to solve. And our multiple choice has our answer there, so we can feel pretty confident if we get the right answer, although there are distractors in multiple choice questions. This next part's called a geometric mean. It's like a geometric average, where when we set up a proportion, two parts of the proportion on either side are equal to each other. Here we're representing that by x. And then there's some other two numbers called the extremes. So if you're asked to find the geometric mean between two numbers, you set those two numbers, one on top and one on the bottom, and the geometric mean, the thing we're trying to find, again gets one on top and one on the bottom of the fraction. So you represent the same number as x, or maybe the geometric mean is a number, but it's the same number on both sides of the equation diagonally from each other. Okay, so here, again, I could use the value y as my geometric mean, and that's the thing I'm trying to solve for, and cross multiplication is the key. You do have to work with a little bit of radical action here, so brush up on how to simplify your radicals before going any further. Geometric means pop up a lot in right triangle problems. So for instance, if you have a right triangle and you draw an altitude from that right triangle to its hypotenuse, it creates two other right triangles inside of it. And that's a nice thing because all three triangles wind up being similar to each other, proportional. And we do this by matching their corresponding congruent angles. So here we get two angles congruent to each other, which I've marked with one arc and two arcs. And I'm going to match those corresponding values in the other triangles by noting where the right angle is in each of these right triangles. Once I have those corresponding parts matched, then these triangles have been drawn so they're oriented in the same direction, so that I can see where the matching corresponding parts are going to go. Now I can write down a similarity statement between the three triangles. Triangle ABC is similar to triangle CBD is similar to triangle ACD. All three triangles are similar. So we can set up proportions between corresponding sides, and angles are congruent, corresponding ones, that is. So this is a very useful tool. I would even say so, especially because right angles, right triangles are used in a wide variety of constructions. And when you set up the corresponding angles, you can find these corresponding geometric means amongst the three triangles, the big one on the outside and the two triangles in the middle. That altitude, which is perpendicular to the hypotenuse of the large triangle, is always going to separate those two triangles. So it'll be a shared side. Now, playing around with this, we're going to get two actual theorems out of this. The first one called the altitude rule. So if we're trying to solve for the altitude in this problem, take a look at the pattern that's comparing the two triangles in the left and the right inside this big triangle. So they both share the altitude side and both have two parts along the bottom of the big hypotenuse. So if we make this little upside down T shape, which is also the shape that we use for perpendicular, we can get this pattern in the right triangle of which parts to set up in a proportion. Now the altitude itself is the shared side, so we call that the geometric mean, the number that shows up on the top and the bottom diagonally in the fraction. So we always have that set up in the problem. Okay, so if we know this is an altitude problem, we start off by identifying what is the altitude. Is it a variable? Is it a number? And that goes twice in our proportion. And then once you cross multiply to solve this, you'll be solving for usually some unknown value. So here in example 1, solving for x, the x is the altitude. So that goes twice in our proportion, one on top, one on the bottom, diagonally. The other two parts, if we make the t pattern or upside down t pattern, are 4 and 12. So we put those into the other two slots of the proportion, cross multiply, and solve. Usually you have to take the square root here. So again, radical action is on. You have to have your game face on when you're doing with your radicals, because they're going to expect you to simplify things in radical form. They don't want the decimals out of your calculator from a radical, unless they ask for it. It is a possibility. All right, the second one, again, the altitude here is in fact the thing we're trying to find. It's the number that shows up on the top and the bottom in the ratio. And you'll notice I chose a different diagonal here to go along, but it doesn't matter. The other two parts are 3 and 15, cross multiplying, etc. With practice, you'll get really good at this. Now, in this case, the altitude is a number, not a variable. So 9 shows up in the top and the bottom, and the other two parts are x and 3. Cross multiplying, and that's actually, if you cross multiply in one direction and then divide, you're good to go, and you get 27 in this case. Again, anytime you need to pause the video, do so you can absorb what we're talking about, get a feel for it, maybe take some notes if you need to. The next rule is called the leg rule, and that's if we use or finding the leg on the outside of the big right triangle and comparing it to one of the smaller right triangles inside. So big guy compared to one of the smaller guys. All right. So if we're looking for the left-hand side leg there, we'd use the smaller right triangle, and the right side one, we'd use the one on the right. Pretty straightforward in terms of diagrams. And so when you set up the leg rule, you'll see that I'm making like this L pattern in the small triangle and on the outside of the large triangle. The L rule, the L pattern. The leg is the part that is the geometric mean, so that always shows up twice in our proportion. Whether it be the left leg that we're looking for, or whether it be the right leg that we're looking for, it's the one that is the geometric mean that's going to show up on both the left and the right hand side of your proportion as equal numbers. A backwards L pattern sometimes comes up, but notice the L inside and the L on the outside. So here we're trying to find a leg, x, and so I'm going to create the L pattern inside that little triangle and the L pattern on the outside of that triangle. So sometimes you have to add up two values to get the big value on the big triangle. So here I had to add up 15 and 5 to get 20. And proportion-wise, you don't really need to explain how to solve cross-multiplying now with any of these. This should be very rote. So the examples is just knowing where to set up your values, okay? So here we have the right leg that's given to us as 6, and so we're going to use that little inside right triangle, and the right and the leg, it's going to be the backwards leg value here. But using your algebra carefully, notice that the big portion is x plus 5. So setting up this is going to involve some distribution, some distributive property. And we're going to get a quadratic equation, again, out of this particular problem. Quadratics, you bring everything to one side, and then therefore you have 0, it's equal to 0. And then you can solve by factoring. Okay, so here we get x squared plus 5x minus 36 equals 0. This is the same quadratic as we considered, similar to what we, look what we were looking at before. And again, you should just practice your factoring if you really want to get good at both algebra and geometry, because quadratics, they show up quite a bit, especially when you start talking about the equation of a circle. So when you have a negative sign on the end constant there, you know that the two numbers that you're going to have in your factors are both positive and negative, or opposite signs. And looking at all the possibilities of two numbers that multiply to 36 here, we're going to find that 4 and 9 is what's going to give us a sum, really a difference, of 5, a difference because they're opposite sign. So x plus 9, x minus 4 are the factors. Setting each factor equal to 0, we get only one positive value, x equals 4. We must reject the negative here because of the fact that it's a length. Stating that BD is 4 because that's what they asked us to find. Well, we're doing well. I hope you're still with me here. We're just going through a couple more leg rule problems. And again, stop the video, pause the video at any time where you need to follow this a little bit more closely, all right? So now here, a lot of the times you have your variable is the leg, and sometimes it's a number, but be very careful. The thing that is the shared side in both the big and little triangle is your geometric mean. Now, when they give you a challenge problem somewhere, it just means that they're upping the level of probably the algebra part. So if it's a leg problem, make sure you piece out all of the things that are going to be in your ratios carefully. Go through it slowly, all right? And setting up our proportion here, you'll notice that there's a few binomials. That's the challenge. Working with some binomials in algebra can be a little bit challenging. I mean, how often do you do it in your everyday life? Okay, so you can summarize these rules here for the altitude and leg rule. You can look at a few examples that I have listed here. And a Regents problem, why not? Let's do one. All right, so here's a multiple choice question. You'll notice the answers all, except for one of them, have a radical involved in them. All right, so that's going to be something that we want to keep in mind. Okay. The altitude rule is what we're looking to find, since BD is the altitude. Cross multiplication, square root action. We get 3 radical 7. In the second example, what is the length of AD? And here, it's a leg rule problem because the altitude is not involved. Carefully looking at our parts, setting up the ratio and the proportions carefully, we have cross multiplying. This is going to give us x is equal to 4. Not bad. Now, similarities in right triangles practice, I really recommend you go through a bunch of problems here and see what you retained. All right, we did cover a lot of material so far, so it's good if you practice. And make sure you're taking a look at both the geometric problems and the numerical problems, seeing that you can do a little bit of both. If you need to draw a diagram, draw a diagram. If you need to label a diagram, label the diagram. And beware of application problems. There might be detailed information in them, like units of measurement to solve for. In a challenge problem, what you want to take a look at is, the level of algebra that they might be trying to throw at you. But in the Regents exam, they're not going to give you challenge problems, okay? Challenge problems, though, are basically Regents level problems. I mean, they really do try to push the envelope and try to get you to think about the next math class you're going to be taking. So next, let's just take a look at some similarities in right triangle, warming up again with some of these problems. Is it the leg rule or the altitude rule? All right, keeping the gears going. Step 1 is to make sure everything is labeled in the diagram, or draw a diagram if there isn't one. Right, and here it's the altitude rule, so we know what to do with that. And you'll become more practiced in it when you just go through and do a couple of problems. You have to do the math to get it. To really know it, you have to do it. Remembering to always look for units of measurement, or to make sure that you've answered the question. Many times there's an X in a problem and you solve for X and realize you needed to go ahead and put that X back in to find the things that might be what they're asking to find. So maybe X helps you find an angle or a side. Quadratic equations with proportions, especially when binomials are involved, can often come up, but embrace them. In Algebra 2, you're definitely going to take on a lot of radicals. And here, leg rule, pretty straightforward. We're letting the leg be y, and we're setting up the parts, finding our answer to be a radical problem that needs to be broken down, square root of 80, finding the largest perfect square in there, and we get 4 radical 5, 4 square root of 5. Again, no decimal values for these. Word problems are typically a little bit more that you have to piece through, take your time with, and draw a diagram. So we have right triangle ABC here, and I'm going to turn it upside down so I can make its altitude so that it looks like the problems I've been working with so far. That altitude is perpendicular, and they call it CD, so I know where my letters are. And I'm labeling where the hypotenuse of the big right triangle is. It says that the segments of that hypotenuse are in a ratio of 2 to 5, and when you see this anytime in a problem, just change it to 2x and 5x, or with algebraic expressions there so that you can make them equal to something. All right, so each of those is 2x and 5x, and we know that we need to find both of these segments in the problem to find the solution to the question. This is an altitude problem, so an altitude rule sets me up here. The altitude is 8, shows up twice in the ratio. Cross multiplying, the x's are actually going to multiply together and square. When you have 2 times 5, it's 10. All right, so just make sure you're multiplying your x's together and getting x squared. Some people make it 2x and make an error there. So when you get a decimal value here, we're going to approximate that, but here when you have to take the square root of a decimal, they're probably going to ask you to round it to a certain number of decimal places. They wouldn't ask you to simplify a decimal radical. But if you keep the numbers as fractions and simplify the radical, that, like I'm doing here in blue, that might be expected of you, and that's kind of a next level thing for you to try to embrace for Algebra 2. In this next problem, they give us another ratio 1 to 9, so I make it 1x and 9x. And in this problem, it's telling me about the altitude, so I know the altitude is involved. So I'm going to use that 6 as an altitude as the geometric mean and put the two parts in my ratio. This is like modeled after the last problem, so I'm really using the diagram, from the last one. And again, you can start to visualize these diagrams in your head when you're doing these problems. And on the Regents exam, they'll become more familiar to you. Here, we're asked to round to the nearest centimeter. So not only do we have units to watch out for, centimeters, we're also going to round them to the nearest tenth. That's 1 decimal place after the decimal. All right, so this is going to be a leg rule, no altitude involved. Leg rule. Now, also, the Pythagorean theorem, anytime right triangles come up, is a very strong possibility, and here we actually need it. So setting up the Pythagorean theorem for that bottom right triangle so we can find the other part there, dB, we can find some pieces here that'll help us solve the problem altogether. Finally, solving for x using the leg rule, we get 36 over 10, which is 3.6. And stating that AD is 3.6 is the part of the word problem, you also want to include centimeters here to round out the problem. So there's a summary here in the packet and on this video that you could pause and take a look at. It's good stuff about solving a quadratic equation and also some similarity of triangle review. So there's a couple of things we can go through here and take a look at this idea of scale factor. So matching corresponding parts is really a big part of similar. As you see here, what we're doing is we're working out the details that in a right triangle there's a 90-degree angle, which means that the other two acute angles always add up to 90. So finding those other two missing angles shows us that the two triangles are in fact similar. And that also helps us match the letters that go together with the similarity statement. Now, to find a scale factor, how big one triangle is to the other, you have to kind of know which triangle was your starting one and which one was your ending one. In this problem, it's not that clear, so we're going to take the left-hand side one as the starting one and the right-hand side one as the finishing one. So if we had scaled the left-hand side triangle to the other one, it would have scaled up. It looks like it's a bigger triangle, and the numbers on the sides of the triangle tell us that it is. All right, so if we scaled the triangle up from left to right, all right, the scale factor can be found by taking the pre-image value, one of the sides of the pre-image, the image, and putting it over the pre-image, the after over the before, and that is the scale factor. So taking the image number, let's say we have 39, and putting that over the pre-image number 26, we get a scale factor of 3/2. All right, so knowing which one is your before and after will tell you about the scale factor. Otherwise, you have to kind of state which one it is. A couple more problems just to consider for similarity. When you can start filling in the missing pieces like a puzzle, the more numbers you get in there, the easier the puzzle becomes. If you've ever done a Sudoku puzzle, the more numbers you start entering, the quicker and easier the puzzle becomes. So here, filling in these angles, we notice that they're not all congruent to each other, which means they're not similar. So we move on. These triangles, however, let's take a look at their corresponding parts, and we're going to match the corresponding legs to, well, let's see. Is it 12 to 9 is to 15 over 12? I would say that makes the most sense, big over small, but they don't cross multiply to equal each other. The triangles are not similar to each other because the proportions, the ratios were not congruent. Here's one that just really needs us to make a diagram. So we have two sailboats. Okay, similar triangles are the sail part of the boats. They give us some dimensions to fill in here. Larger sail, 10 by 24 by 26. Smaller one has a smallest side of 6, that's all they tell us. And they want to know what the perimeter of the smaller sail is. So they're drawing on the idea that the ratio of the perimeters of the two objects are equal to the ratio of two corresponding sides. And since 10 and 6 are corresponding sides, we can use them to answer the question. So the perimeter of the smaller one works out to be 36. Again, most of the time we're talking about ratio and proportion. Make sure you include your units here. They're talking about measurements in feet. Again, when you don't have a diagram, you really need to draw one. Now, you could do certain problems without them, but I really think for geometry, you're doing yourself a disservice if you don't draw and label yourself a diagram carefully, neatly. Take your time. A, B, C, and D, E, F are the ordering on the two triangles. I try to orient them in the same way. We want to find DF, which is equal to Y, and then also find AC. Setting up corresponding parts is proportional, cross-multiplying, solving for Y. And once we find Y, we can then plug that into Y plus 10 to give us AC. So since Y is equal to 6, AC will be equal to 16. No units on this one. Algebra or algebraic expressions always mean that you're going to have some kind of an equation to solve. When it comes to geometry, those algebraic expressions represent sides or angles, and there's relationships or equations that go along with those things. Now, if we're trying to find x in this problem, which is DE, cross-multiplying, we have to be careful. A little distributive property. Collect like terms. Solving for x, we get 4. And therefore DE is equal to 4. Recall the parallel lines in a triangle, let's say segment, that is to a parallel to a side, that is. We have similar triangles, proportional side splitter parts. So you can look at the ratios and always expect that sometimes you have decimals or fractions. We do prefer fractions. But if you're more comfortable with decimals, make sure you write them in the right way. 18 2/3 would be 18.6 repeating. Some problems look very complicated, but they're really not. So you see parallel lines, you know about parallel lines and transversals, you know a lot about them. You know about corresponding angles, corresponding parts. There's a lot that you can start to connect here now that you're well practiced in geometry. Connecting the algebra here is why we use algebraic expressions, getting you to solve equations, continuing to do that. That's an important part of mathematics. Equations are relationships. So as we build geometry, what we're really doing is learning the concepts drive the equations. The equations are modeled after things that we've solved in algebra. We use algebra to solve equations, and so we bring together algebra and geometry at the end of this course. It's a pretty good bet that when you're solving an equation in geometry, that many things are equal to each other, or they add up to some specific number. Proportional things can usually be pretty easily visualized. Corresponding parts, as long as things are oriented in the right way, can be matched pretty easily. Anytime you have right angles or parallel lines, you have symmetry, and things that you can exploit, that symmetry can show up as an equation. Things that are congruent to each other, that are equal to, happen because of symmetry. And so what I hope you've gotten out of a lot of this video here and this review is that the driving force behind similar triangle problems is the proportion. And knowing how to set up a proportion and use a proportion will serve you pretty well. I mean, if you're baking a cake, you need to maybe double the recipe. You're solving proportions by changing the ingredients all in the same amount, all in the same way. The angle bisector theorem here with the proportional sides. We're just going through a couple of review problems here. Again, this is just more for you to kind of view and review and kind of take in and see many different examples so that when it comes time to take that Regents exam or that geometry final exam, this will seem like old hat. And when you do something more than 26 times repetitively, you create a habit for it. And good habits, at least momentarily here, will serve you well when you take the Regents. You want it to be habitual when you read something and you look at a problem that you know what to set up. You don't have to think about that. That's the learned part already. It's not too late to embrace mathematics in your own life, even if you don't see yourself as a mathematician. Learn the patterns, learn the rules, learn to solve the equations. There's something very satisfying about solving a puzzle, which really math problems are. And the more you do, the smarter you become. The more sharper your brain becomes. You can see more patterns, and the more patterns we can kind of see in things, the more relationships that we can build. And isn't that the point? Anyway, let's get back to some mathematics. So here I'm just going through problems with the leg rule, just noticing patterns. I'm not really trying to focus on the details of the algebra because we've done it. It's a moot point here. We're not teaching algebra, we're looking at the relationships, we're looking at the bigger picture, because that's what geometry really does. It helps us look at the picture and the bigger picture, and then the bigger picture, and then the even bigger picture. Is there an end? That's the beauty of the discovery. We don't know. That's what we're here to find out. So keep looking, keep exploring. And when you're doing a review for a Regents exam like the one we're doing here, it's good to take a break every once in a while and come back with fresh eyes, walk away. So here let's take a look at an extended response problem, a Regents level question, where they've given us a diagram. Some of the things have been marked, but we're going to include our own markings here, x and x plus 6. And setting up a proportion here, I mean, if you read through the problem, you'll see why I chose x and x plus 6. And the entire thing, if I put that together, is 2x plus 6. So again, drawing on our algebra skills, we get a quadratic equation. This might be like a part 4 question you would see on a Regents exam. And seeing how good your algebra skills are is probably something they may test this year on the Regents exam. We reject any negative answers in geometry when it comes to lengths, so x equals 2. And plugging that back into the expression for AC, we get AC is equal to 10, and I should have put meters at the end of that, but I think I forgot that, so I would have got a point off on the Regents. Anyway, thanks folks. You've been great. If you'd like to subscribe to my YouTube channel, it's Figure It Out, and I hope you subscribe.